Could one tiny particle, almost impossibly small, rewrite our understanding of the entire universe? It sounds like science fiction, doesn't it? But sometimes the universe throws us a curveball. This isn't just a story of subatomic particles, it's a story about our quest for knowledge. Imagine the grand tapestry of physics woven with threads of gravity, electromagnetism, and the nuclear forces. We call this understanding the Standard Model. It's been incredibly successful, explaining so much of what we see and what we don't see. But what if a single thread, a tiny, almost insignificant observation, began to unravel a small part of it? What if that unraveling pointed towards something even grander, something new? This is the tale of the Muon g-2 experiment, an experiment designed to test the Standard Model with extreme precision. It involves a particle called a muon and a mysterious property known as its magnetic moment. Scientists at Fermilab, a powerhouse of particle physics in America, have been watching these muons, and what they've seen has sent ripples of excitement throughout the world of physics. So, what exactly is this mysterious particle, the muon? Think of the electron, that familiar workhorse of the atomic world, powering your lights, running your computers. Electrons are fundamental particles. They are leptons. Muons are also leptons. They are like the electron's bigger, heavier cousin, about 200 times more massive in fact. This extra heft makes them quite interesting and quite useful for certain kinds of experiments. Muons are not particularly stable. They don't hang around for long. An average muon lasts for only about 2.2 microseconds. After their short life, they decay. They transform into other particles like an electron and some ghostly neutrinos. This instability is actually a feature, not a bug, for experiments like Muon g-2. Their quick decay provides the signals that scientists are looking for. Where do muons come from? They rain down on us from the atmosphere. Cosmic rays, high-energy particles from space, strike the upper atmosphere. These collisions create a shower of other particles, and muons are among them. Now let's talk about something called the G-factor. Many fundamental particles, like electrons and muons, have a property called spin. You can imagine them as tiny spinning tops. This intrinsic spin gives them a magnetic moment. They act like incredibly tiny bar magnets, with a north and a south pole. When you place a tiny magnet in an external magnetic field, what happens? It tries to align itself with the field. It might wobble or precess around the direction of the magnetic field. Think of a spinning top wobbling as it slows down. The strength of this internal magnet and how strongly it interacts with an external magnetic field is characterized by this G-factor. For a simple point-like particle with spin, theory initially predicted its G-factor should be exactly 2. But the universe is rarely that simple, especially at the quantum level. The vacuum of space isn't truly empty. It's a seething soup of virtual particles constantly winking in and out of existence. These fleeting particles interact with the muon. They form a little cloud around it. And this cloud of virtual particles slightly alters the muon's magnetic moment. It changes its G-factor from exactly 2. For decades, physicists have been trying to measure the muon's G-factor as precisely as possible, and they've also been refining the theoretical calculations from the Standard Model. The previous major experiment at Brookhaven National Laboratory in the early 2000s hinted at a discrepancy, a tiny difference between what was measured and what was predicted. But the hint wasn't quite strong enough to claim a discovery. There was still a chance it was a statistical fluke. Then came the Fermilab Muon g-2 experiment. With a more powerful beam, more sophisticated detectors, and an incredibly precise magnetic field. In April 2021, they released their first results. The new measurement confirmed the Brookhaven findings. The muon's wobble, its magnetic moment, was indeed slightly stronger than the Standard Model predicted. The experimental value was just a tiny bit larger, but a tiny bit with huge implications. This difference, this anomaly, might seem minuscule to an outsider. We're talking about a deviation in the 9th or 10th decimal place. But in the world of particle physics, precision is everything. The Fermilab result, combined with Brookhaven's, pushed the statistical significance of this discrepancy to 4.2 standard deviations, or 4.2 sigma. So how do you actually measure something as subtle as a muon's wobble? Well, you need a very special machine. At Fermilab, the heart of the Muon g-2 experiment is a giant electromagnet. A storage ring, 15 meters or about 50 feet in diameter. This isn't just any magnet, it's a superconducting marvel, cooled to incredibly low temperatures. This allows it to create an exceptionally uniform and intense magnetic field. This precision is absolutely crucial for the experiment. First, scientists need a beam of muons. They start by accelerating protons, the hearts of hydrogen atoms. These protons smash into a target. This high-energy collision creates a shower of new particles, including particles called pions. These pions are unstable. They quickly decay into muons. The muons are then carefully guided, using magnetic fields, into the storage ring. They are injected at nearly the speed of light. Once inside the ring, the powerful magnetic field takes over. It forces the muons to travel in a circle. But remember, muons have spin. They are like tiny spinning magnets. So, as they race around the ring, their spin axis isn't fixed. Why all this fuss about a tiny wobble? A minuscule discrepancy in some obscure number? Because this isn't just about the muon. It's about the entire framework of fundamental physics. The standard model for all its successes is known to be incomplete. It doesn't include gravity, for instance. It can't explain dark matter, that mysterious stuff that makes up most of the matter in the universe. It doesn't tell us why there's more matter than antimatter. These are huge gaping holes in our understanding. The muon g-2 anomaly could be the first crack, the first experimental evidence pointing directly towards physics beyond the standard model. If new, undiscovered particles are indeed influencing the muon's magnetic moment, then those particles must exist. They must be part of a larger, more comprehensive theory of nature. Finding such particles would be revolutionary. It would be like discovering a new continent on the map of reality, a place we never knew existed. Many theoretical physicists are incredibly excited by these results. They have proposed various extensions to the standard model, theories like supersymmetry, for example. Supersymmetry suggests that every known particle has a heavier superpartner. Some of these hypothetical supersymmetric particles could interact with muons, and they could explain the observed g-factor anomaly. Other theories propose new fundamental forces or even extra dimensions of space. The journey of discovery is far from over. The 4.2 sigma result from Fermilab is incredibly promising. It's a strong hint, but it's not yet definitive proof of new physics. To reach the gold standard of 5 sigma, scientists need more data, much more data. The Fermilab experiment is continuing to run. It's collecting vast amounts of information about muon decays. Each new decay event helps to refine the measurement, to shrink the uncertainties. The team at Fermilab is meticulously analyzing this new data. They are also re-examining every aspect of the experiment, checking for any potential systematic errors, tiny effects that could mimic the signal of new physics. This is painstaking work. It requires incredible attention to detail, because the stakes are so high. They want to be absolutely sure before they claim a revolutionary discovery. Science demands rigor, especially when challenging a well-established theory. Simultaneously, on the theoretical side, physicists are working hard too. They're trying to improve the precision of the standard model prediction for the muon's g-factor. This calculation is incredibly complex. It involves accounting for all the known particles and forces, and how they contribute to the muon's magnetic moment through those virtual particle loops. So we stand at a fascinating crossroads in our exploration of the universe. A tiny, fleeting particle, the muon, has presented us with a profound puzzle. Its subtle wobble, its magnetic dance, doesn't quite align with our best current theories. Is it a herald of new particles, new forces? A sign that our standard model, as magnificent as it is but a stepping stone to a deeper, more complete understanding of reality? The evidence is mounting, the excitement is building. The universe is under no obligation to make sense to us, or to conform to our neat equations. It is what it is. Our job, as curious explorers, is to observe, to measure, to question, and to listen carefully to what the cosmos tells us, even when its whispers are faint, even when they come from the almost imperceptible behavior of a subatomic particle. The muon g-2 experiment is a testament to human ingenuity, our relentless drive to push the boundaries of knowledge. What an extraordinary thought, that by studying these infinitesimal constituents of matter, we can learn about the grand architecture of the cosmos, about its origins.